we're looking at hypergeometric probability. And are there some blank notes in your sheet? Probably the things that are highlighted in red. So key thing about hypergeometric, repeated trials are not independent. So we're not replacing the event. So every single time we're drawing, the probability is changing. So obviously, the more times you draw, it's affecting your next result. So that's why they're not independent. So your first time you do it, that affects your second result. When that's the case, we're moving into hypergeometric, and it reviews what that formula is. Probability of, we define our x, the number of successful outcomes we're talking about. In our previous question, the number of 2 yellow marbles, x represented the number of yellow marbles. It was going to be the total number of ways we could choose yellow marbles, which is the total number of yellow marbles, choose 2, and then the remaining unsuccessful marbles, b. The 2 numbers on the bottom, x plus n minus x, that's going to add up to our total number that we're choosing, right? So that's why it was like 2 plus 3 to give us a total number of 5 marbles that we were choosing, divided by the total number of ways we can draw 5 marbles. So that's the review of the formula. So that was assuming we only had 2 outcomes, success and failure. So that was on Friday. So today what we're going to be looking at is what happens if we have, say, 3 outcomes. So we've got, now instead of calling success and failure, it's just like success 1, success 2, success 3, right? They're just 3 different events that we're talking about. So this is the general case of the hypergeometric probability distribution. On Friday, we looked at a specific case where there were only 2 outcomes. Here we're looking at 3 or more. We won't go beyond 3, but this formula would extend. Sure. Okay, we'll take a look at this in an application. Our expected value remains the same. This is the same formula that was given in on Friday. The key thing here is that when we're talking about an expected value, we'll only be talking about the expected number of one of the elements. So we're not going to be going with what's the expected value of 2 yellows, 1 red, something like that. We're going to say, what's the expected number of yellow marbles? Or what's the expected number of black marbles? Or what's the expected number of blue marbles? It's only going to be the expected number for one of the options that we're talking about. All right, so our example here is what is the probability that a bridge hand of 13 cards contains 6 spades? So we got 13 cards in total, 6 spades, 4 hearts, and 2 diamonds. So if we let our x represent the number of, so we're going to have x1, x2, x3. Let x1 represent the number of spades, x2 represent the number of hearts, and x3 the number of diamonds. Let x1, x2, x3 represent the number of spades, hearts, and diamonds. Oh, and one club, thank you. So we need X4. Diamonds and clubs, thank you. So therefore our A, B, C, and D are going to represent the total number of each of those suits. The total number of spades, total number of hearts, total number of diamonds, and total number of clubs. So A is going to be 13, which is the number of spades. B is again 13, number of hearts. C is 13, which is our number of diamonds. So these are the total number that we can be choosing from. And then D is 13, our number of clubs. So now we write this as saying our probability of X1 equal to 6 spades, our X2 equal to 4 hearts, our X3 equal to 2 diamonds, and our X4 equal to 1 club. The probability of that happening, we can use our formula, but it's going to be the number of ways I can draw 6 spades times the number of ways I can draw 4 hearts times the number of ways I can draw 2 diamonds times the number of ways I can draw 1 club. All of those cards add up to 13. So that's our 13 card hand. So that's the number of ways I can be successfully drawing 6 spades, 4 hearts, 2 diamonds, and 1 club. And then the total number of ways that I can draw my 13 card bridge hand. There are 52 cards in the deck. Choose 13. When we do that, it comes out to 1716. Therefore, there is a 0.2% chance of having a bridge hand with, what was it, 6 spades, 4 hearts, 2 diamonds, and 1 club.